ovaj tjedan.
Da, dogovaramo se za moj...
Da, to mi i mene zanima, da te pitam na dan.
Petak od 9 do 12.
Ali tjedan iza neću moći u petak.
To gledamo sad ovaj, idi.
Ok, sljedeći
jedan pojen.
Dobro je, ok, hvala. I will come back now once more to the methods of this solving this simple least square problem. One method is to square and solve the linear equations. GT, V, G, Z is equal to GT, TF. This is a linear problem with a positive definite matrix, GTWG, which can be solved by standard methods, Gaussian elimination or Kolesky decomposition. Kolesky. That means GTWG, excuse me, Z equals to GT, G prime times W times G times G. In the MATLAB notation. This may have some shortcomings if the matrix which we here have, usually we call it K or A, has a very high condition number. It can happen if it is nearly singular. Then we can come back to this equation and solve directly. Z equals to V times times G which automatically computes this minimum. MATLAB knows about that. And there is another way which may be recommendable in special situations. And this is to make the singular decomposition, singular value W 1/2 G is equal to U sigma 0 VT. Well, U and V are orthogonal matrices of corresponding dimensions. And sigma is diagonal. Sigma sigma S. S is this dimension of matrix G. This is the number of parameters in least square problem. Well, usually we arrange those sigmas like sigma 1 larger or equal sigma 2 larger and so on. Well, we expect to have sigma s to be greater than 0, which means that the matrix sigma together is positive definite, and which means that this matrix G and W1/2 G has full rank. It's equivalent. So now we have sigma 0 Z prime plus ut double u1/2 f is equal to minimum. Well, z prime is equal to vt z, and this is equal to sigma minus 1 g1. Well, ut w1/2 f is equal to g1 g2. In making this equation here, we use the fact this u is orthogonal. So multiplying inside the norm of with an orthogonal matrix does not change this norm. So that means now that you have sigma 1 g1 prime is equal to g1, sigma 2 sigma s g prime s is equal to gs. The first thing is that you can now get the solution just by dividing by singular values, which is not worth the whole thing because the singular value decomposition takes some time. But now you can look, what if some sigmas are very small? First of all, the condition number of this matrix is square root of the condition of this matrix. So if there are very small eigenvalues here, there will be better singular values here. Because the singular values of this matrix are the square roots of the eigenvalues of this matrix. Singular values of sigma I.e. of are eigenvalues of Vg by definition. So you see, here you treat, so to say, the squared problem with squared condition number. And here you are more cautious. But still you can have very small singular values. So what you do then? Then you look at the right-hand side. If the right-hand side is also very small, then you just can drop those lines out of the solution. It's rubbish. And keep only those which were large enough. How large? That's the user matter. The user has to decide. And now this is an introduction, some to say, to a big field of application which is called dimension reduction. You use, in fact, for many points, You use only a couple of parameters to represent them. But this number of parameters can be even much smaller if you find that your singular values here, which you found here, are small. Dimension reduction is the term. I am sure that you will hear quite a lot of this with Professor Damac. Well, there is one more question which may sort of worry you here. We had points and we had, I come back to the matrix x1, 1, x and 1 we had at the beginning with the line. So what if the condition number of this matrix is small? That means, well, that those x's are almost equal. So that means that you have things, something like that. Well, but then in this case, look at the y's. If they are very good separated, then we have made a wrong question. Instead of represent those points as a function y of x, do it as a function x of y. Change the role of the coordinates and everything is good. So that's the point. Well, it can happen that even then you are badly. Because then if just all points are about one point without any other pattern, then nothing has to be done. But you can change the coordinates in this case. We'll come back to this point after. If xy almost equal to xj, then change the roles of x and y. And try then. My next question is now a bit different. We had mentioned L infinity approximation, L1 approximation, and L2 approximation. And it is L2 on which we have concentrated. Now the question is there any real, non-trivial reason why use and when use L2? Well, you would say, well, I take L2 anyhow as a first approximation to L1 on L infinity. That's another bad idea because it can be computed. And with those two, you will have somehow to iterate, like Newton or something like that. And when you're using these iterations, the most difficult issue is the first starting point. Quite important. Find a good starting point. And then the least squares can deliver this starting point. That's one interesting issue. But I would like to somehow touch a more fundamental question with why and where and when the least squares are natural. Well, the people would tell you, well, least squares would be recommended if you make measurements for a function which you know to be linear, but you don't know those a and b. But you know that the model you are measuring is linear. And you know that in measuring you make errors. And those errors may have some character. And usually the measurings are independent. And independent measurings, so one says, lead to what? To a sort of Gaussian distribution. Gaussian distribution has to do with independent measurings. So, the difference between the true value AXI plus B, which lies on the line, and the measured value, Y1. So the difference should be distributed in Gaussian way. That means that we have then the density of distribution, everybody knows that, sigma I e to the minus AXY plus B minus YI square over 2 sigma I. This is the Gaussian distribution density with standard deviation sigma I. So now what is the density, probability density, if you make n experiments in an independent way? Well, we know that it's a product of the probabilities and also of the densities. So this will be then product I is equal to 1 to n, 1 over 2 pi sigma I e to the minus AXI plus B minus YI square over sigma I square, 2. Now, when this is maximal probability, when this is minimal, which, now this is simple, I make pi I 1 over n, or excuse me, the number of points is always capital N. 1 over 2 pi sigma I, this is now a constant. But now, here we have just e to the minus some AXY plus B minus YI square over 2 sigma I. So now this is a constant. Maximize this means minimize this. And these are least squares. Weighted least squares. With weights, Vi is equal to 1 over sigma I. Yeah. Leads to sum I AXI plus B minus YI square over 2 sigma I square equal to minimum. So, that's easy. So once we suppose that we have Gaussian density probability density in our measurements, it leads automatically to least squares. But now we would now switch to 1 degree up, third degree. Why Gaussian? What has Gaussian distribution to do with independent measurements? Well, there is a theorem telling about that, a big one. That's the abbreviation, CLT. And the meaning is central limit theorem. Central limit theorem. Well, I'm far from it now to make any serious proof of it. But I will try to convince you that it is true. I had quite a lot of moments in my study where I saw the proof and I was able to reproduce it, but I was not convinced. I almost thought I was cheating. I was cheated by somebody. Well, everything is okay, but you have a bad feeling, and this feeling for a mathematician is just as important as checking the full proof. Bad feelings are not good. So I'm now going to try to convey to you some good feelings, hoping that you will then believe me. Okay. So why Gaussian? I think this theorem is one of the eminent achievements in mathematics. Why Gaussian? Well, so you make your measurement with some probability distribution, which is given by a function p greater or equal to 0 on r, such that the integral p dx is equal to 1. Some other measurement or measurable properties, I will not skip them. Take just p a beta continuous function with compact support. That's enough. Then all integrals are well defined. So now, repeating our experiments gives distribution which is a product. Px1 times Px2 in R2. So now we would now look the distribution of the mean value of both of them, x1 plus x2. That is Pt is equal to 1/2 for mean value integral over Px1, Px2, Px1, Px2. And the integral goes over x1 plus x2 less equal than t. This is the probability that the mean value is less than t. And this will give us then the probability density for this quantity. Starting with this and take new variables. x1 equals to u and x2 equals to v minus u. We're changing variables. You must look after the Jacobian. And this is 1. The determinant of this transformation is equal to 1. So dx1, dx2 will be equal to du, dv, roughly speaking. So now we would have 2 dt equals 2. By changing the variables, integral over du over everything, and then integral from 0 to t, from minus infinity to t, p u p v minus u. And now we can change the integration, because this now is a constant, doesn't come up in the integral. dv integral over r p u p u. So this now is the density. If this is probability, then you just cancel the integral and get the density. So new density will be p hat integral pu over p v minus u d u. So, and what's that? This is a convolution. So repeating measurement or experiment which has a given distribution independently leads to a new distribution, which is the convolution of the first one with itself. So we can write down p hat is equal to p star p, the star in the convolution. That's just squaring in the convolution sense. And so on, if you continue. Third power, and so on. So we have to look, and that's what the central limit theorem is about, to behavior of the powers of convolutions. And that's far beyond of what I can do here. But I can show you how the convolutions behave in computing them. So let me now try. It's always a problem with MATLAB. Oh. Možete meni pomoći kako ću ja promijeniti direktori da MATLAB zna da mora samog stika računati, a ne odavde.
Možete da gore promijeniti.
Tu gore? Aha, samo malo da vidim. Da, samo moram vidjeti koje. Ovo je adresa tu. Onda mora biti E, jel tako? samo malo, dakle E,
Ne morate ručno, imate ove.
Probajte vi, ha? Ajde. Aha, bravo. Tu je to, dobro, bravo, aha. Transport, tako je, onda 2021, jako dobro, on ima još malo, kurs, GIFs, GIFs, sam malo češće pokazao GIFs. Evo ga GIFs, jako dobro. Tu smo sad, jel tako? Da vidimo. Ne, nije. Nešto ne valja.
Aha. Ovaj tu želite otvoriti.
Tako je, da. Ok.
Samo povećati.
Ja bi ga potjerao.
Ne, samo da povećamo se ne vidim.
Aha, ne. Dobro.
Neko zna da se povećava.
A pa dovoljno je ovo, nije strašno. Ako gledate, ako metnemo ovako, evo ovo bolje, jel? Dobro je, da vidimo. To nije komandni prozor, samo malo, ovo. To, tako je, da. Ovo ćemo maknuti, to nam ne treba, ali sad je bolje. Evo ga. Dakle, da vidimo najprije kako to izgleda. The program is simple. It gives the x-axis and gives you then the possibility to put in the function which you wish, and then it just iterates the convolution. You see this conv. You iterate the convolution. Okay. So CLT. So let me give you something. For example, this function. This is a simple distribution. That means this is 1 minus absolute value of x minus 0.5. That's what it is. So, no. Octave did it. MATLAB won't. What is that?
Imaju oktava tu.
Da, to nema smisla. Malo Oktava radila, samo čas da vidimo. Ja bi MATLAB maknuo. Okay, yes. Save change, no. Okay.
To vam je na desktopu. Samo spustite.
Što, molim? Da ovih se maknemo, ne treba nam, ja?
Spustite, da.
Dobro.
Evo ga.
Bravo. Sad moramo opet
Otvoriti
direktorij, jel? Evo ga. Ok. Ok. Aha. Tu, jel? Ovdje, ne.
gore, ovdje ova strelica zelena.
Aha, okej. Aha.
Ili ovaj plavi tu.
Ovo, jel?
Folder.
Mhm.
Evo ga. Dole.
Tako je, jako dobro. Jako dobro. Evo ga, izvrsno.
I to je to, select folder.
Ok. CLT, dobro je. Smo rekli smo 1 minus absolute value of x minus 1.5. That's what it is. P. Okay. Mhm. So. It did the whole approximation in one step. So let me change different versions of, it did everything, but so fast that the whole iteration was done in a second. There must be an editor here. Let me see. Editor, where is the editor? Okay. Pause. Okay. Save file, good. Okay.
Tu dole.
Command window, yeah, okay. So you see how it approximates the Gaussian curve. In three approximations we are there. Okay. Can you give me any function? Let's take a random. Okay. P is equal to a random of what? Of size of x. Size. So. Čarobnjakov učenik. Ne da se zaustaviti. Samo malo. Mahmud. Okay. Run. Okay. So. Gaussian. Well, not always the things are so fine. Not always. It will. Okay. There are too many.
Možete zaustaviti, mislim sad se trebalo sve.
Stvarno ne znam kako se da ne može zaustaviti. Metno sam previše iteracija. I'm very sorry for that.
Pritisnite Ctrl, Ctrl i C.
Okay. Okay. Now, let's now take some another example. P is equal to absolute value, but taken to the fourth power. That's also probability. a very uncommon one. You see, the convergence is there, but it happens as a mean value. The mean values converge. And that's the contents of the theorem in the general case. You see, after some iterations, it becomes better. Why? Because of rounding errors, which smooth the function. Those cases in practice are extreme cases, which the functions have discontinuities, and then the convergence is small, is slight, and only in a mean value sense. So after some time it becomes better and better. Well, as I saw that, I was convinced that the Gaussian function is the solution of the problem. But the proof is a big deal, and it needs quite a lot of knowledge, a good analysis. And I would recommend, if you wish to make sometimes the proof, one of you may get it as an examination work. To take the book, a very old one, is some 70 years old, but a classic. Probability theory. By William Feller. By the way, he was student of this university here. And after 2 years of study in Zagreb, he already made his doctoral dissertation. And went to Göttingen, submitted it, and got his degree there. And he was one of the founders of the rigorous theory of probability, Kolmogorov and Feller. And this book by Feller is, in my opinion, a masterpiece of good analysis, and you can do the proof of this theorem in many different ways. Some of them are more probabilistic in their approach. His approach is more analysis, operators, Fourier transform, for example. That's what he does. I like it quite a lot. And I think I taught it 2 years ago here I had a course on Fourier analysis, and I included the proof of this theorem as an application of Fourier analysis. Well, so let's stop now. I would make a small stop, some 10 minutes, something like that. Okay?